Hello, this is Final Exam Screencast question number 5. I'm Kevin Reynolds, and we're going to jump right on into it with an overview. So what we're going to start off with is the concept of molecular recognition and the idea of protein and ligand with regards to molecular recognition. Then we're going to look at two different rates, the rate of association and dissociation. Then we're going to emphasize why dissociation is very important to this. Then we're going to give kind of a concept of fluorescence and isotropy and how that relates. And then finally we're going to finish off with bound versus ligand concentration relations graphically. So, as mentioned, we're going to start off with molecular recognition. And what this kind of, in a sense, is and how we're going to look at it is an introduction of a ligand to a protein. So on the bottom here we see this red figure. This is what's going to be considered our protein. Now, what's going to actually happen is we're going to have our blue figure, our ligand, and it's going to be introduced to it. So moving forward in the reaction this way, what we see is an association, or the coming together of, and we get the creation of our entire molecule itself. Now, dissociation obviously is the opposite of association, and we get a negative correlation where we're going to actually break it apart. Now, both of these play a different role, and how it's going to show up is we're going to look at the actual dissociation rate. So, in looking at the dissociation rate, we're going to kind of, in a sense, set it equal to the association rate. What's kind of the significance of this and why the dissociation rate is kind of important for when we look at these different calculations and equations is that the KD is actually the non-reciprocal or the reciprocal of the association, but it gives us actually a flat term and we don't have to do any more mathematical things. It also has a thing where it tends to prioritize or move towards the separation of the protein and the ligand, so we see the separation, whereas association, you're kind of in a sense calculating the overall association, the overall creation of our protein ligand molecule, which, yes, it's important, but not always the most important. So with understanding that, looking at the two individual parts themselves can be really important. We get an ode to fluorescence and isotropy. In anisotropy, the concept that rotation and size matters are very important. Larger things move slower or spin slower, and smaller things spin faster. So looking down here at the bottom, we have our old protein, and then we have our protein-bound ligand. One of the big important things that we're looking at is the concept with FA is the actual rotation. This item on the left, just our protein itself, is going to spin a lot quicker than our item on the right, which, with our item on the right being what it is, it's important to understand that we can actually get a value for this, calculate a value for this, and understand it a little bit more, which is what FA actually helps us do. Now, the kind of last little tidbit we're going to go over for a little bit is the concept of a bound protein and ligand versus just the ligand concentration. Now, the graph in white, which is just a negative relationship between the two, is indicative in looking at a really nice, even relationship between it. But that's not always how it works, and the concept of cooperativity, whether it be positive or negative, actually plays a role. So to look at the red first, we're going to look at positive cooperativity. Now, what positive cooperativity, in essence, is showing is the ability that when ligand initially begins to bind, it takes a little bit quicker to get to the protein, but once it gets there, it actually speeds up all of the surrounding ligand binding. The opposite is seen in negative, where on this little experience right here, we see that it takes really quickly for the ligand to actually start to bind to a protein, but once it's bound, it actually slows down the rest of the binding. This is unfortunate and not something we actually want to look at or have, so that's why positive cooperativity is more beneficial than negative cooperativity, unless you had a reason why it wouldn't be so.